Before we move on to the next topic, let us quickly recall what we discussed in the previous lecture. And if you recall, in the previous lecture, we talked about the continuous time signals and discrete time signals, and we saw a few types of the continuous and discrete time signals. And the first type that we discussed in the last lecture was the real sinusoidal signal, which has this form as x of t equals a cosine omega naught t plus phi, or we can also use the notation theta. Okay, so a denotes the amplitude, omega naught denotes the frequency, and phi or theta denotes the phase shift. And similarly, we saw the discrete equivalent of the real sinusoid, where it is denoted as x of n in square brackets, which is equal to a cosine omega naught n plus phi or theta again. Okay, now the distinction is that in continuous time signals, the function x of t is defined for all values of time, whereas for the discrete case, the function x of n is only defined for integer values of n. That means n can take only integer values. We cannot have x of 1.1 or x of 1.8 or x of 2.3. No, it has to be only integer numbers. So for the discrete sequence, n takes on only integer values. And then we also discussed the real exponential signals. Again, we saw both the types, continuous time exponential signal and the discrete time exponential signal. Again, the general form of the exponential signal is x of t equals c e power a t, where when c and a are real numbers, we get a real exponential signal. So the real exponential signal is obtained by putting values of c and a to be some real numbers. And we also discussed the case as to what the exponential signal looks like when this exponent a is positive, or when it's negative, and when it's equal to 0. Okay, we have discussed this in the previous lecture. And then we also saw the real exponential signal in the discrete time, where we denote this as x of n in square brackets as c alpha power, and again, instead of c e power a t, it's c e power some letter n, but that letter is beta in this case. Okay, c e power, instead of a t, it's beta n, but for convenience, this e power beta can be written as alpha, and that makes this function as x of n equals c alpha power n. Okay, now again, we saw what happens, or what does the signal look like for different cases of alpha. When alpha is greater than 1 or less than minus 1, in other words, when the magnitude of alpha is greater than 1, or the case when alpha is between 0 and 1, or between minus 1 and 0. That is the case when the magnitude of alpha is less than 1. Okay, we have seen what happens. Okay, we get something like the growing exponential or the decaying exponential, and so on. So that was discussed in the last lecture. In today's lecture, we are going to move on and extend the ideas of the signals to the exponential signals when c and alpha, or c and a, take on complex numbers or complex values. Okay, we will see what happens for the continuous exponential signal when this c and this parameter a are, instead of real numbers, they are complex numbers. So we'll see what happens in that case. And similarly, for the discrete case, we'll see what happens when the c and alpha are complex numbers. And we'll also see a special case where this beta is purely imaginary. Okay, so when we set beta to be purely imaginary, it gives us a special kind of signals. So we will be discussing all of these in this particular lecture. So that is what we call as the complex exponential signal, and in the first instance we will discuss the continuous time version of the complex exponential signal, and later on we will see the discrete version of the complex exponential signal as well. Now the general form, as we've seen earlier, is c e power a t for the complex exponential signal. Now, because we are dealing with complex exponentials, these parameters c and a are going to be complex numbers. Now, when we had these as real numbers, we got real exponentials, which we saw in the previous lectures. These are the plots that we had for the real exponential signals. Okay, when a is 0 or greater than 0, and when a is less than 0. That is, when a is positive and when a is negative. We see where for a is positive, it's a growing exponential, and when a is negative, it's a decaying exponential. Right. Now, today we will focus on the case when c and a are complex numbers. So when we make these parameters c and a as complex numbers, we can represent these complex numbers either in the polar form or in the rectangular form. And what we are going to do is we are going to represent the parameter c in the polar form and the parameter a in the rectangular form. So in the polar form, you represent a complex number by its magnitude and phase. So the magnitude of this complex number is magnitude of c, and the phase of this complex number c is denoted as theta. So we have in polar form as the magnitude and phase. Magnitude e power j times the phase. And in the rectangular form, we represent this in terms of the real and imaginary parts. So you have the parameter a represented in rectangular form as a equals r plus j omega naught. So r is the real part and omega naught is the imaginary part of this complex number. Now, we are just going to substitute these values for c and a in the general expression for the exponential signal. So the general expression is x of t equals c e power a t. So for c, we are going to substitute this in polar form, magnitude of c e power j theta, and in place of a, we are going to put this complex number in the rectangular form as e power r plus j omega naught t. So r plus j omega naught is nothing but a. So a t, right? Now, we can expand this function and get this in a more intuitive form. So the magnitude of c e power j theta. Now e power r plus j omega naught t, we can write that as e power rt into e power j omega naught t. Now we can combine the j terms. E power j theta and e power j omega naught t can be combined together, and that will give us magnitude of c into e power rt, and we are going to combine the terms which have j in the power. So we can write that as e power j omega naught t plus theta. Okay, so that's the complex exponential in the general form when we substitute the parameters c and a as complex numbers. Now what we are going to do is we are going to expand this using what we call as the Euler's identity or the Euler's relationship. E power j something is given by an expansion. We are going to substitute that expansion and see what this x of t looks like. So the Euler's relation is given as e power jx is equal to cosine x plus j sine x. So in place of x here, we have omega naught t plus theta. This is e power jx, right? So the x term is here, omega naught t plus theta. And that can be expanded as cosine x plus j times sine x. So we get this complex number in the rectangular form with the real part as cosine x and the imaginary part as sine x. So using this relationship or the Euler's relation, we are going to expand e power j omega naught t plus theta, which is this term, e power j omega naught t plus theta. So that becomes cosine omega naught t plus theta plus j sine omega naught t plus theta. Now, substituting this expansion in our x of t, so we can expand this part as cosine omega naught t plus theta plus j sine omega naught t plus theta, and both these terms are going to be multiplied with this factor, which is magnitude of c e power rt. So that will become magnitude of c e power rt and e power j omega naught t plus theta can be expanded in this form, which is here. So that will become cosine omega naught t plus theta plus this magnitude c e power rt is also multiplying the other term, so that's a common multiplying factor to both these terms. So plus because there's a j term here, so we'll have that j magnitude of c e power rt into sine omega naught t plus theta. So that becomes our expansion for x of t, which is the complex exponential. And now we have this in the rectangular form as sum a plus j times b. So we have this as our real part and this as our imaginary part of this complex number. Now we will see that we notice that because this x of t, when c and a are chosen as complex numbers, we see that the x of t that we get is indeed a complex number which has a real part and an imaginary part. Okay, so that's our that's the real part, and the part which is with the j is the imaginary part. So that's the real part of the complex number, and that's the imaginary part. Okay, so x of t is indeed a complex signal. So that we have what is called as a complex exponential signal, which we have represented in the rectangular form. Now we are going to analyze what happens to this, or what form this signal takes for different values of r. So by setting r to specific values or ranges, we are going to get different types of signals. So you'll see what happens when r is equal to 0, when r is positive, when r is negative, and so on. So we will see the different cases and analyze the complex exponential for different combinations or different values of the parameter r. So the first condition that we are going to deal with is when this parameter r is equal to 0. So when we set r equal to 0 in this complex signal, so e power 0t, and here also it becomes e power 0t, and that is e power 0, here also it's e power 0. The e power 0 is 1. Okay, any number to the power 0 is 1, so that term becomes 1. So we get simply as c cosine omega naught t, or the magnitude of c cosine omega naught t plus theta, plus j times the magnitude of c sine omega naught t plus theta, because this e power rt becomes equal to 1. So let me mark that. So when r is equal to 0, that's equal to 1 in this particular case. Okay, so again we now still have the complex signal, but now the real part has this amplitude or multiplying factor magnitude of c, and the imaginary part also has this magnitude of c as the multiplying factor. So basically what we see is that this magnitude of c is just going to be a number. So it is some number multiplied by cosine omega naught t plus theta plus j times some number into sine omega naught t plus theta. That means the real part of the complex exponential when r equal to 0 is just a cosine signal. So the real part is just a cosine waveform, and the imaginary part of the complex exponential when r is equal to 0 is just a sine wave. So we have a cosine wave as the real part and a sine wave as the imaginary part of the complex exponential when the parameter r is chosen to be equal to 0. In other words, what this means is that when we set r is equal to 0, okay, that means we are setting this parameter a to be purely imaginary. So if you notice from the previous slides, a is r plus j omega naught, and when this r is equal to 0, that means we are saying a is equal to j omega naught, which is just purely imaginary. So there is no real part. This is a complex number which has the real part and imaginary part. When we make the real part to be equal to 0, what we are left with is only the imaginary part. So that means setting r equal to 0 is basically constraining that the parameter a is purely imaginary. So in that case, we get a complex exponential which has its real and imaginary parts as sinusoidal signals. In specific, the real part is going to be a cosine waveform and the imaginary part is going to be a sine waveform. Okay, and sine and cosine are together referred to as sinusoids. Okay, when we say sinusoids, it can mean sine or cosine or even shifted versions of sine and cosine, because when you shift the sine wave by 90 degrees, you get a cosine wave and vice versa, right? So the sinusoid, by sinusoids we mean sine or cosine waves without a shift, or they can have shifts by themselves. Okay, but the wave shape will look something similar. They might have different phase values nonetheless. Next, we are going to see what becomes of this complex exponential x of t when we set the value of r to be some positive value, that is r greater than 0. So we see what is going to happen to the waveform or the signal x of t. So when r is greater than 0, that is r is positive, then the complex exponential signal, which has this form, c magnitude of c e power rt cosine omega naught t plus theta plus the j magnitude of c e power rt sine omega naught t plus theta. Now here r is chosen to be greater than 0, so e power rt is going to be a growing exponential, right? So e power rt for r positive is going to be increasing in its envelope. So it's a growing exponential. That means what is happening is the real part of the complex exponential is getting multiplied with some parameter, some function, which is a growing function, because each time we increase time, as time increases, we will notice that this value keeps on growing. So the real and imaginary part is getting multiplied with a growing exponential in this case when r is positive. The magnitude of c is a fixed number. Magnitude of c here also is a fixed number, but e power rt is going to keep on increasing as t increases. So as we see here, as t increases, the e power rt term is increasing and increasing and increasing, as we see in this dotted line, and similarly here it's increasing in the negative direction, right? So that's minus c e power rt. So the envelope or the boundary or the border of this waveform is increasing exponentially. So what we see here is that when r is positive, the real and imaginary parts of x of t are sinusoids, which is cosine and sine, but they are multiplied by a growing exponential, okay, as we have plotted here in this graph here. So when r is positive, we see that it's a growing exponential, and this dotted line, it denotes this multiplying factor c e power rt. This multiplying term is shown here in the dotted line, and what you have on the upper side, the upper envelope, is plus c e power rt, and on the lower side, the lower envelope, is minus magnitude of c e power rt. Okay, so when r is positive, we have the real and imaginary parts being multiplied by growing exponential. Next, we will see the case when the value of r is less than 0. So we have here what happens when the value of r is less than 0 or negative, right? So in this case, this e power rt term is going to be a decaying exponential. So as t increases, e power rt is going to become smaller and smaller. So these terms here in the real and imaginary part, e power rt, they represent decaying exponential, and that occurs when we choose r to be negative, that is less than 0. So what we see is that with r less than 0, the real and imaginary parts of the complex exponential x of t is going to be sinusoids. So we have a cosine here and a sine here, both are referred to as sinusoids, and they are multiplied with a decaying exponential. So that means the overall amplitude as t increases, that is as we move forward on the time axis, this amplitude of this sine and cosine is going to keep on decreasing. Okay, what I have shown here in this plot is only for the real part. Okay, I have shown for the cosine, right? Similarly, for the sine, it will look the same except that it will start from 0. Okay, the sine wave starts from 0 rather than starting from the peak. It will start from 0 and move forward. Okay, like in this case. So you see this cosine starts from the top and that completes one cycle. But the sine here, it starts from 0 and completes one cycle here. So that would be the imaginary part. The sine is the imaginary part and the cosine is the real part. So here also I have shown the growing exponential with the cosine term, that is for the real term. Similarly, for the imaginary term, it's going to be the same shape except that it will start from 0 and keep oscillating. Okay, and that's exactly what we have here also for the case when r less than 0, where it is a decaying exponential, and I have shown here for the real part only. Okay, so that's for the cosine term. Similarly, we can have it for the imaginary term, which will have the sine waveform starting from 0 from here. Okay, now again, as before, the upper envelope is the positive magnitude e power rt, and the lower envelope is the negative magnitude of c e power rt. Okay, so we have seen what happens for to the complex exponential when we set the value of the parameter r to different combinations, like r equal to 0 or r greater than 0 or r less than 0. Now, the first case that we saw, that when we set r equal to 0, that is an important class of complex exponentials which will be used throughout this course in many of the tools that we are going to use for analysis. Some of the mathematical tools that we use for the analysis of signals and systems and in signal processing, they use these complex exponentials where the parameter a is purely imaginary. That means we set r equal to 0, so that gives us a equal to j omega naught, and we've seen what happens to those to that complex exponential. The real and imaginary parts are sinusoidal signals, but they are multiplied only with a constant factor. They are not exponentially growing or decaying. They have a constant amplitude, the constant peak amplitude, right? A constant envelope, that is. Okay, so they form an important class of signals or complex exponentials that we will discuss in more detail, and they are like the fundamental building blocks in some of the tools that we are going to use. When I say tools, I mean analytical tools for the analysis and processing of signals and systems. Okay, so it's an important class of signals when you have r to be purely imaginary. And for simplicity, I'm just going to make this term magnitude of c to be equal to 1 and this theta to be 0. So we'll just say there is no phase shift and this amplitude is 1. So that makes the signal as simply cosine omega naught t plus j sine omega naught t, which makes the notation more representation more compact. But in general, it applies even with the phase. Okay, even if you have some amplitude and some phase shift, the observation is that this particular signal, when we have a to be purely imaginary, is a periodic signal. Now, what do we mean by periodic signal, and how to compute or calculate the period of a signal for both the continuous case and the discrete case? I will be discussing that with examples in my next lecture. But for this lecture, I'm going to focus only on introducing to you the different types of signals and what their behavior is, or how they look like. Okay, and once we are familiar with all the signals in this lecture, in the next lecture we can start investigating into the properties of those signals and also some of the transformations that we can do with those signals. Okay, so the important property here when we have the parameter a in c e power at to be purely imaginary is that we get a periodic signal. The real and imaginary parts, or just the complex exponential itself, is periodic. Okay, so we have the complex exponential as c e power j omega naught t plus theta, so that is periodic, and even when the phase is 0 and the amplitude is 1, we still get it as periodic. Okay, so irrespective of the magnitude and phase, e power j omega naught t is going to be a periodic signal, and that is an important property for that particular case when r equal to 0. Now, just as we are able to represent the complex exponential e power j omega naught t in terms of the cosine and sine waveforms, we can also represent the cosine and sine waveforms in terms of the complex exponential, okay? And we are going to do some simple trick here to represent the cosine omega naught t in terms of e power j omega naught t, and similarly sine omega naught t in terms of e power j omega naught t. And that comes in handy at times when we are performing some calculations. So you need to know how to represent the cosine and sine, because cosine is a real signal, the sine is also a real signal, but this real signal is in the imaginary part of the complex signal, right? So we want to know, we want to see how we can represent these real signals in terms of the complex signal e power j omega naught t. So for that, we'll bring up the concept of complex conjugate. And again, that is something you should be familiar from your background of complex numbers, okay? The complex conjugate of e power j omega naught t is e power minus j omega naught t. So in terms of the rectangular form, we just change the sign of the imaginary part. That gives us the complex conjugate. So e power j omega naught t is cosine omega naught t plus j sine omega naught t. If we replace this plus with a minus, we get the complex conjugate of this particular term. And in the polar form, we have it as e power, we just change the sign of the power from plus j omega t, we make it as minus j omega naught t. So we have this equation 1, which is denoting the e power j omega naught t that we have seen, and the complex conjugate of that is e power minus j omega naught t, which is cosine omega naught t minus j sine omega naught t. Now, we want to express our sinusoidal signals, cosine and sine, in terms of these complex numbers, in terms of these complex exponentials. So what we are going to do is simply add these two equations. When we add these two equations, equation 1 and 2 together, we get e power j omega naught t plus e power minus j omega naught t on the left hand side. And on the right hand side, when we add these two, this plus term and minus term is going to cancel out. So we are going to get left out with only cosine plus cosine, which is 2 cosine omega naught t. So we have now cosine omega naught or 2 cosine omega naught t as e power j omega naught t plus e power minus j omega naught t. So we can now bring this 2 to the other side, to the denominator, and write our cosine omega naught t in this form as e power j omega naught t plus e power minus j omega naught t divided by 2. Or I can take that 2 as a separate factor, factor it out, and we get it as half e power j omega naught t plus half e power minus j omega naught t. Okay, so by adding these two, the complex exponential and its conjugate, we are able to represent cosine omega naught t in terms of the complex exponential signal. Similarly, we will represent the sine waveform in terms of the complex exponentials by subtracting equations 1 and 2. That is, we are going to make equation 1 minus equation 2. And when we do that, when we subtract 1 minus 2, we get e power j omega naught t minus e power minus j omega naught t, right? And that will give us, when we subtract this cosine term will cancel out, and minus of minus will become plus, so this term will add up. That will become 2j sine omega naught t. So that is exactly what we have here. And now taking the 2j to the other side, we have, and we can represent our sine omega naught t as the sum of two complex exponentials. Okay, so we have seen how to represent our real sinusoidal signals in terms of the complex exponential signals. Okay, now what we want to realize is, in a complex number, the real part of the complex exponential signal is the cosine term, and the imaginary part of the complex exponential is the sine term. So in other words, we just say that cosine of a function, cosine omega naught t plus theta, or cosine x, or sine, similarly sine omega naught t plus theta or sine x, we can represent each of these as cosine being the real part of a complex exponential, and sine being the imaginary part of the complex exponential signal. Okay, so this is just different ways of looking at the same thing. Okay, how we are trying to represent the same thing in different ways, because when we are trying to analyze things, sometimes it becomes more convenient to look at the or represent the signal in one form rather than a different form. So we should be familiar with all these different forms of representing the same signal. So we have seen how what does a complex exponential look like, and we have seen how we can represent our real signals, real sinusoids, in terms of the complex exponential. So here we have represented our cosine signal as the in terms of the complex exponential signal, but here I have included the amplitude as well as the phase shift theta. So the amplitude is A and the phase shift is theta. Now with this, we have this form for our real cosine signal in terms of the complex exponential. So it's a by 2 e power, instead of 1 by 2, it's a by 2 because we have a here, and instead of e power j omega naught t, we have j omega naught t plus theta because we have a plus theta term here. Okay, and now we can separate out the j omega naught and j theta terms. Okay, e power j omega naught t into e power j theta. All right, so that gives us the complex exponential here in terms of omega naught, and we have split out and represented our cosine omega naught t in terms of e power j omega naught t. Now I want to leave it as an exercise for you to do the similar thing for a sine omega naught t plus theta. So when we have a sine omega naught t plus theta, how would you have a similar expression, or what would the similar expression in this form would look like for a sine omega naught t plus theta? Okay, so it's a very straightforward thing, and I'll leave that as an exercise for you to work it out. Okay, and as I said before, the cosine term is the real part of the complex exponential, and the sine term is the imaginary part of the complex exponential. And because the amplitude is a, the real part gets multiplied by a, and because the amplitude is a here, the imaginary part gets multiplied by a. Okay, now let us move on into the similar discussion for complex exponentials, but for the discrete case now. So we're going to now look into the discrete complex exponentials case. So or in the complex exponential signals in the discrete time. Now again, the general form for the complex exponential in discrete time is x of n in square brackets to be equal to c alpha power n, and this alpha is e power beta. Okay, now when we choose these parameters c and alpha as complex numbers, then we are going to get the discrete complex exponential signal. So we are in the case of continuous signals, we represented c in polar form, and r the parameter r there in rectangular form. But now here for the discrete case, we are going to express both c and alpha in polar form, and then expand our signal and see what it looks like for different combinations of alpha. Okay, so we are going to denote the parameter c in polar form as magnitude e power j theta. So the magnitude of c and the phase of c is theta, and similarly the parameter alpha is going to have its magnitude as magnitude of alpha, and its phase is omega naught. Okay, so we have represented both in polar form, and now we can substitute these in our general expression for the discrete complex exponential, and that gives us magnitude of c e power j theta. That's for c. In place of c, we are substituting this term, and in place of alpha, we are substituting this term, and alpha is raised to the power n. So this magnitude of alpha should go to the power n, and e power j omega naught should also go to, should have the power n, right? So it's alpha power n e power j omega naught n. So now we can just combine the terms, and so we can have magnitude of c alpha power n, and this e power j terms can be combined together to give it as e power j omega naught n plus theta. Okay, and if you notice in the previous lecture, for the discrete case, I denoted the frequency as omega naught, okay, and it's the same as omega naught, okay. Only when we have to deal with the discrete and continuous case in the same problem, to distinguish the discrete frequency with the continuous frequency, we will use the different notations. But when that distinction is not needed, then we'll simply use the small omega naught, okay. So for the frequency, all right. So they can be used interchangeably, unless we want to have a clear distinction that, in this particular problem, this omega naught means discrete frequency and this omega naught means continuous frequency, and so on. But where this distinction is not needed, we will just use the same notation, okay. That's only a case of notation, it doesn't matter. So our complex exponential in the discrete time takes this form, okay. So again, because it's a complex exponential, it can be written now using the Euler's expression. E power jx is cosine x plus j sine x, right? So in place of x we have omega naught n plus theta. So we get with this term cosine omega naught n plus theta plus j times, again the multiplying term, sine omega naught n plus theta. And because it's a complex signal, we have a complex number in rectangular form now. It's a plus jb form, right? So we have the real part and the imaginary part of this complex signal in the discrete case. And again, the important thing here is that the parameter n, or the index n, takes on only integer values. We cannot have non-integer values for n, okay. Now, just as in the continuous case, we will examine the signal for different values of alpha, okay, because magnitude of c is just going to be a number. Now it's we can set this alpha to, which has a which is raised to the power n, we can set this to different values and see what happens to the discrete complex exponential signal. Of course, we cannot have alpha to be equal to 0, because 0 power anything will become 0, and this whole term will be 0, and this whole term will also become 0, because it will have 0 as a multiplying factor. So we cannot have alpha to be 0. So the first case that we are going to look at is for the case when alpha is equal to 1, okay. So let's look at that. So when the magnitude of alpha is equal to 1, we get alpha power n. So 1 power n, and 1 power any number is 1. So that alpha term will disappear. So what we get is, this is a cosine sequence and a sine sequence multiplied by a number which is magnitude c. The magnitude of any parameter or any number is just the number, right? So basically we get the real and imaginary parts of this complex sequence as sinusoidal sequence. So the real part is going to be a cosine sequence and the imaginary part is going to be a sine sequence. So that is exactly what is here, and I have shown the real part in this diagram, okay, which is a cosine. The imaginary part, it will start from 0 and move upward like this, okay. So the sequences of the signal for the real and imaginary part of x of n are going to be sinusoidal sequences when the magnitude of alpha is chosen to be equal to 1. Now next we will see the case when the magnitude of alpha is greater than 1. So when we have magnitude alpha greater than 1, then as n increases, for a number which is greater than 1, say 1.5, 1.5 power 0 is 1, 1.5 power 1 is 1.5, 1.5 power 2 is 2.25, and so on, right? So this alpha power n term is going to be growing exponentially. So that means the real and imaginary parts of this sequence x of n, which is this cosine term and the sine term, they are getting multiplied with some factor which is exponentially growing. So when the magnitude of alpha is greater than 1, we get the real and imaginary parts of x of n that are sinusoids, or sinusoidal sequences in this case, that are getting multiplied with a growing exponential. So we get the sequence something like this, where as n increases, we see that the amplitude of these terms, of these samples, are getting bigger and bigger and bigger. So they are exponentially growing, okay, because it is getting multiplied with the term which is exponentially growing. Again, in this diagram, I have shown you for the cosine term, which is for the real part. Okay. Similarly, for the imaginary part, it will look in the same form, except that instead it will start from 0 rather than starting from a peak, from a higher peak. It will start from 0 and move upwards and downwards. Okay. So it will have a sine form for the imaginary part, and it has having a cosine form with the growing envelope as n increases. Okay, let's see for the case when the magnitude of alpha is less than 1. So when we have alpha less than 1, that means that number is something like 0.5 or something. So 0.5 power 0 when n is 0 is 1. 0.5 power 1 is 0.5. 0.5 power 2 will become 0.25. So that means, you see, as n increases, this term is becoming smaller and smaller. So that corresponds to decaying exponential. So in that case, when the magnitude of alpha is less than 1, we see that the real and imaginary parts are again sinusoidal sequences, but they're getting multiplied with the decaying exponential. So the net effect is that we get a complex signal whose envelope is decaying exponentially. So we see this decaying exponential thing. Okay, again, I have shown it for the real part, which is cosine. If it's a sine, it will have the sine form, where the first sample will be 0 and gradually it will keep increasing and then decreasing, right? So that's the form the complex exponential sequence takes when our magnitude of alpha is chosen to be less than 1. Next, we will see another important class in the discrete exponential signal. Just as we saw the important class in the continuous exponential, where we chose r to be 0, here we are going to constrain beta to be purely imaginary. Okay, since alpha is equal to e power beta, so c alpha power n is c e power beta n. Now this beta term can be made purely imaginary. So if there is no real part to this beta, so this alpha, which is e power beta, will become e power j something, right? So c alpha power n, c we have written in what do you call it, in the polar form, and e power beta n, and beta is now purely imaginary. It's just j omega naught. There is no real term here. It's completely imaginary. In that case, we get the complex exponential sequence x of n in this particular form, which is having e power magnitude of c e power j omega naught n plus theta. So we have just combined these two terms because they both have this common j term, right? So the j has been taken common as a common factor, and it's omega n plus theta. Now from the Euler's relation, we have this omega n plus e power j omega n plus theta as cosine omega naught n plus theta plus j sine omega naught n plus theta, which is getting multiplied by this magnitude of c term, right? So when we set this beta to be purely imaginary, we get these complex exponential sequence x of n in this form, where we have this cosine sequence as the real part and the sine sequence as the imaginary part, which is getting multiplied by a constant. So that means it is not exponentially growing or exponentially decaying, but it has a constant envelope. And secondly, the important property of this particular sequence is that it is periodic. Okay, again, what is the meaning of periodic, and how do we compute the period of a signal? I will, as I said before, I will be discussing that with examples in the next lecture. Okay, but for now you should understand that the special case of important class of signals, when beta is purely imaginary in the discrete case, we get a discrete complex sequence which is periodic. All right. Now, as in the continuous time case, where we expressed the sinusoidal signals in terms of the complex exponential, we are expressing now again the discrete signal, the discrete sinusoidal signal, in terms of the complex exponential sequence. And we are using the Euler's relationship here also. So we can represent the in a way similar to what we did in the continuous case, where we took e power j theta and e power the complex conjugate e power minus j theta and added the two terms, right, to get the cosine term. So similarly, we can do that in the discrete case. The only difference now is that instead of t here, the continuous variable, you now have n, the discrete index. Okay, so we can now represent the discrete sinusoidal sequence in terms of the complex exponential sequence in this particular form, and we've done it in a similar way just as we did in the continuous case. Okay, and again here I will leave it as an exercise for you to work out what would be a similar expansion or representation of the sine term, okay, in terms of the complex exponential. I'll leave that as an exercise, and again, as in the continuous time case, the cosine term can be represented as the real part of the complex exponential, and the sine term is the imaginary part of the complex exponential. And when it's having an amplitude of a, that real part, the imaginary part, gets multiplied by that particular parameter of factor a, which is the amplitude of the signal. Okay, so far in today's lecture, we have discussed the complex exponential sequences for complex exponential signals for the continuous time and the discrete time, and we've seen what their behavior is for different values of the or choices of the parameters. Now we will move on to a new class of signals that are very, very important in signals and systems and in signal processing. And the first important type of signal that we are going to see is it's called as the unit impulse function, and I'm just going to first talk about it in the discrete time and also represent the continuous time version of that signal. Okay, and we denote the discrete time unit impulse. In fact, the unit impulse, whether it's discrete time or continuous time, we use the letter delta to indicate that it is a unit impulse function. Okay, and the definition of this function is that it has a non-zero value only when the index is 0. So when n is 0, its amplitude is 1. For all other values of n, its value is 0. So x of n or delta of n is equal to 1 for n equal to 0. So when n is 0, we have it value equal to 1. And when n is not equal to 0, for whether it's positive or negative, x of n or delta of n is equal to 0. Okay, so it has a non-zero value only when the index n is equal to 0, and that is called as the unit impulse function. And in the discrete time, we write it as delta of n, and obviously for discrete, n takes on only integer values. Okay, and the unit impulse function is also called as a unit sample function. So when you say unit impulse or unit sample, it means the same thing. Okay, and very often we will use these terms very interchangeably. So, and it's an important type of signal that will be used very extensively in this course. So have a clear understanding of this. So the impulse function is defined only when the index is equal to 0, and for all other values of the index, the impulse function takes on a value of 0. Okay, as we have seen here. And sometimes the impulse function is also called as the delta function because we denote it by the Greek letter delta. It is sometimes also called as the delta function. So it means the same thing. So it has three different names. It can be called as unit impulse or unit sample or even delta function sometimes. Okay, now let's have a look at this unit impulse function in the continuous time. So in the continuous time, we have time as our independent variable, and we denote the unit impulse continuous time function as delta of t. And again, this function has a non-zero value only when t is equal to 0. For all other values of t, that is when t is not equal to 0, the impulse function delta of t is 0. So it has a non-zero value only when delta is only when the time index is 0. Okay, now instead of the amplitude being 1, we can multiply the delta with some constant, with some number. And so let's say if we write it as 5 delta of t, that means this amplitude here will become 5. If we write it as, say, some k times delta of t, then this amplitude here will become k. Okay, so that is just a multiplying term, but in general delta of t alone is having an amplitude of 1, but if you multiply the delta of t with some number, the height of that impulse at that index will become will take on a value of that multiplying factor, whether it's 5 or any other number k. Okay, so the impulse function can have different amplitude, but when we say unit impulse, it means unit amplitude. That means amplitude is 1. Okay, I'm going to erase that. And similarly, even for the discrete version, so if we say as say 5 times delta of n, 5 delta of n, then this amplitude will be 5. If it's 8 delta of n, then this amplitude will be 8, and so on. Okay, so that is something, just a multiplying factor to indicate that the amplitude of the signal is 1. But when we say unit impulse, it means unit amplitude. Unit means 1 amplitude. Okay, so we have seen the unit impulse function for the continuous time case and also for the discrete time case. Now let us look at the next type of signal that is important in our course. It's called as the unit step function. Okay, it's called a step function because it has like a step shape. Okay, it is having one value up to a certain index, and then the value goes up as a step. It is climbing in one step and it remains there for the rest of the time. So that's called as a unit step function. And again, if you notice here, the unit step function, when you say unit, it means the non-zero amplitude is equal to 1. And the definition for the unit step function is that it has a value of 1 for n greater than or equal to 0. That means from 0 to any higher value of n, when the index n is 0 and above, then the amplitude is 1, and for negative values of n, the amplitude of the signal is 0. Okay, so the unit step function has a non-zero value of value equal to 1 for when n, or the index n, is positive or 0. For negative values of n, its value, the signal or the samples of the unit step function, they take on the values of 0. Okay, and again I've shown it from minus 10 to plus 10, and this could be for going on and on. Okay, and going on and on, it can keep going in this direction and in this direction. Okay, so if we keep going to the right, you'll continue having more lines like this. Okay, so that's the discrete time unit step function, which is defined as or represented as u of n. Because it's discrete, it's in square bracket, and for the unit step function, we generally use the notation of u. Okay, u of n is 1 for n positive or 0, and it's 0 for n negative. Likewise, we can have this u of n, say, multiplied with something. Okay, suppose I have, say, 8u of n, then this amplitude, instead of 1, it will become 8. Okay, in that case, it is not a unit step function, it is just a step function with an amplitude 8. When we say unit step function, its amplitude is 1. And similarly, we have the continuous time version of the unit step function, which we denote as u of t, and that is equal to 1 when t is 0 or positive, or when t is negative, the unit step function takes on a value of 0. So as we see here, and if you can see it very clearly here, it's like looking like a step. So that's why it's called as a step function. And if this term is multiplied with some number, then this amplitude here will have that multiplying factor. So if it's 5, then this value, this step here, will have a value of 5. If it's 8, it will have a value of 8. Okay, but when you say unit step function, it's going to have an amplitude of 1 for t equal to 0 and positive, and when t is negative, it's going to have a value of 0. And the general notation here again is u to represent that it's a step function, and because it's continuous time now, it's the independent variable is time in parentheses or round brackets. Okay, now let us just summarize the contents of today's lecture. And what we have discussed is, we have discussed about the continuous and discrete time signals, and we just had a quick overview of real signals, okay, which was from the previous lecture when we talked about real sinusoidal and real exponential signals. And within the exponential signals, we saw the growing exponential and the decaying exponential. And today's focus was mostly on complex signals, where we talked about the complex exponential signals. And within the complex exponential signal, we saw that the real and imaginary parts could be are sinusoidal signals, and the sinusoidal signals could be having a growing or decaying exponential term multiplied to them. Okay, and then in the last part, we talked about the unit impulse function for the continuous as well as the discrete case, and then we also talked about the unit step function for both the continuous as well as the discrete case. Now, in the next lecture, I will go into more details of these signals and investigate some of the properties of these signals. So, for the complex signals, you'll see some properties like the periodic. I said that it has an important property called periodic. So, what do we mean by periodic signals, and how do we compute the periodicity of the signals? And then we'll also see how we can represent the unit step function in terms of the impulse and vice versa. Okay, so we'll discuss all of this in the next lecture.